Hello and welcome back to Exoplanets 101. So today we're talking about another detection method, and that is direct imaging. So direct imaging is actually one of the easiest detection methods to understand conceptually because it's what you might exactly think of when you think of detecting an exoplanet. It's just taking a picture of it. However, that is a lot easier said than done. So the challenge with imaging an exoplanet is that exoplanets aren't very bright and they're located next to something that is very bright, and that's a star. So not only are you trying to observe something that's very dim, but it's being overshadowed by this enormously bright object right next to it. So you need to be sensitive enough to the light to detect these dim planets, but have some way of blacking out that starlight, which is going to otherwise overwhelm the image of the exoplanet. I don't want to get too much into the details of how we do this, but there are devices such as coronagraphs or star shades that can be basically used to block out the star's light, and then we can actually image the planets that are around a star. Now, light can come from a planet in two different ways. So the first is that it can reflect light from its star. So for example, think about the moon in the night sky. It's really bright, right? But the moon isn't emitting that light itself, it's just reflecting sunlight. And the other way is that some planets can actually emit their own light strongly enough to be detected. Basically, every planet does emit some amount of its own radiation, usually based on its temperature. But that's usually a very, very small amount. For example, for the Earth, that would be a very negligible amount. But for some planets, that's quite large. And so we call these planets self-luminous, right? So they're not just reflecting the sun's light, they're actually emitting their own light, so they're self-luminous. And with the limits on our current technology, self-luminous planets are actually the only kind of exoplanets that we can currently directly image. So we cannot see planets that only are reflecting light from their host stars. So this would basically be any kind of terrestrial or rocky planet. Which is a shame because those are really interesting planets, but there are still a lot of awesome and interesting planets that we can directly image. Because the amount of radiation that is emitted by a planet is related to both its size and its temperature, that means that we can most easily see very big, very hot planets. And when I say big, I mean really big, mostly bigger than Jupiter. So in fact, there's a lot of overlap with the brown dwarfs. So with direct imaging, a lot of times you'll hear the term companion or planetary mass companion instead of a planet, because a lot of times the things that they're observing might be brown dwarfs or they might be planets. And so there's a lot of kind of gray area on whether or not some of these things are planets or not. So besides just being sensitive to very big, very hot planets, like I said, we also have to black out the light from the star somehow. And that process of blocking out light from the star also kind of blocks out the very inner parts of exoplanet systems. And so there's a certain point at which you just cannot see the interior of a system via direct imaging. And this is called the inner working angle. So while this blocks us from seeing close-in planets, it does allow us, it means that we can see these planets that are farther away from their host stars. And if you think back to the other detection methods that we talked about, most of them are most sensitive to planets that are very close to their host stars. So direct imaging is a very complementary way of observing systems that can give us information about these outer reaches of the system that we just couldn't detect via, say, radial velocities or transits. But we can try to observe some of the same systems using both methods, and that can help us build a more complete picture of an entire system. So planets are very hot when they first form. As they gravitationally collapse in on itself, that gravitational energy turns into heat, and then that heat is emitted away. So when I say that we're sensitive to very hot planets, that means that we're sensitive to very young planets. So for direct imaging, we're frequently trying to target very young stars that are going to have these very massive planets that are just starting to cool and contract. And so they will be the brightest and easiest to detect. So what kind of information do we get about a planet when we directly image it? So basically we're seeing the light that's coming from that planet, and so we can get a spectra of the planet. So a spectra is just basically the power or the flux that's being emitted at a given wavelength. And you can look at this over a range of wavelengths, and that gives you a spectra for a planet. The spectra can tell us things like the temperature of the planet, and it can also give us information about the composition of the planet, because certain molecules and atoms interact with light in very specific ways at a given wavelength, and so when we see signals there, we know that that molecule or atom must be present. So this can tell us information about the atmospheric compositions of these directly imaged planets. We can also see how far away a planet is from its host star. Now this is just a 2D projection, right? So this is just the distance in the sky plane. So it's not necessarily its orbital distance. But if we observe the planet for a long enough period of time, we can watch it move, and then we can actually construct its orbital elements. Now this is really interesting, but it's actually only been done for one planet so far, and that's Beta Pictoris b, because it has a short enough period and we've observed it for long enough that we actually have seen enough of its motion to reconstruct its orbit. But it's very cool to be able to watch in real time a planet orbit its stars. This is an image of the HR8799 system, which is a very famous directly imaged system that has multiple giant planets in it. These planets are also in resonance, which I'm not going to get into this video, but it's very cool, and this is a real-time, I mean sped up, but this is actual detected images put together to make this movie of the planets moving that we can actually see. So this is really cool. I think this is one of my favorite things. So cool. And then because we get the brightness of the planet, we can actually use models to infer a mass for the planet. But this is a really uncertain process because it's depending on a lot of values that we may not know very well, and it's depending on our models, which may not be perfect models. So we get masses, but they're usually very uncertain masses with a wide range of uncertainty. And a lot of times, as I mentioned before, that range of uncertainty encompasses brown dwarfs. Brown dwarfs are not planets. We're kind of skirting the edge of planetary territory with direct imaging with our current technology. So unlike a lot of the other methods that we've talked about, direct imaging isn't necessarily sensitive to the orientation of the orbit. For example, for transits, we said it has to be a very edge-on orbit because we have to see the planet pass between us and the star. But if you're just taking a picture of the orbit, it could be anywhere. It could be directly edge-on or it could be face-on for any given single detection. However, because there's an inner working angle and we can't see the things that are close to the star, if a directly imaged planet is transiting its star or is close to edge-on, it will pass through that inner working angle for a large part of its orbit where we wouldn't be sensitive to it and we wouldn't be able to detect it. Whereas a planet on a face-on orbit, we would be sensitive to detecting it for its entire orbit. So even though we could detect a planet in a face-on or edge-on orbit, there's more likely that we will detect planets with face-on orbits just because they're visible for their entire orbital period, and unlike edge-on planets. So that's a little bit of a sensitivity bias, but not necessarily the same way that transits are a very strict bias, if that makes sense. So the very first exoplanet that was detected by direct imaging was in 2004, and this was 2M1207b. Now this is actually an interesting exoplanet because its host star is actually not a star, it's actually a brown dwarf. This goes back to what we talked about in the very first video in this series of what makes a planet, or what makes an exoplanet, and does it have to be in orbit around a star, or can it be in orbit around a brown dwarf? Does this indicate that it may be formed differently? There's a lot of implications for this, but this is a planetary mass object, so I will consider it an exoplanet for this series. It's a very large planet, like I said, we're most sensitive to these very large planets. It's about 3 to 10 times the mass of Jupiter. This goes back to, again, we get very uncertain masses based on the luminosities of these objects. So anywhere between 3 and 10 times as large as Jupiter, which is a pretty big range, but a very exciting detection and discovery nonetheless. And so I've mentioned a lot in this video the limitations of our current observational technology. So this is a big goal for the exoplanet community. There was a recent study done to prioritize the exoplanet community's desires basically going into the 2020 decadal, which is a survey or a kind of study of the entire astrophysical community and what we hope to see in the next 10 years as far as, space missions and priorities for astronomy. So the exoplanet community did our own individual one to kind of feed into the larger community of the astrophysics decadal. And one thing that was really stressed in the exoplanet study, and one thing that I personally feel very strongly about, is directly imaging planets in reflected light. So as I said earlier, we can only see right now planets that are self-luminous. So these are going to be very giant, very hot planets, which are very interesting on their own. But if you're curious and interested in planets like the Earth, which many of us are, then you need to be able to see planets in reflected light. And we want to be able to see planets in the habitable zone, which means we need to get pretty small inner working angles so we can see the inner parts of a system where there could be a potential Earth analog. So I think this is really important, and so do a lot of other astronomers. And hopefully we'll start to see this sort of technology coming online in the next few decades. It certainly is within reach, even though none of our current facilities are capable of it, but definitely this is kind of the next big step, I think, in exoplanet detection. We'll be directly imaging terrestrial planets or other planets in reflected light in the habitable zones of other systems. But for now, we love our giant planetary mass companions that we've discovered via direct imaging. So of the 4,306 confirmed exoplanets as of November 2020, 51 were detected via direct imaging, and so that's only about 1% of the total. So this is not right now a very large portion of our detections, but it is a very exciting portion of our detections, and it's a very unique section of parameter space, so we wouldn't be able to discover these planets via some of these other methods. That's direct imaging. I hope you learned something about how we actually take pictures of exoplanets, and I hope I will see you again next week.